Okay. Yes. So I'm gonna present some of the work we are doing on the scalable deep neural network training. LBANN is being developed at Lawrence Livermore National Lab for the last several years. I joined Livermore about 2 years ago. The project existed at the time and joined the project because it seems interesting. But you may wonder why DOE Lab needs to develop their own framework, despite that there are many existing ones like TensorFlow, Caffe, PyTorch, and our LBANN is not as, I mean, if you want to just have some the easiest to use tool, you probably don't want to look at LBANN. Maybe the project lead may not agree with that, but yeah. So, but there's still a gap that we need to address, and also there are opportunities that are not fully leveraged in the existing framework. So that's the main motivation of our work. So this is the particular focus of my work within the project is on making this run faster on our big machines like Sierra. So I'm mainly going to talk about the performance issues and scaling issues of the LBANN. So these are the main people I'm working with. Nikolai Dryden, who was a Ph.D. intern at Livermore from UC. He just recently graduated, and I think he already studied as a postdoc at the ETH Zurich in the Thorsten Wolfroth group. Yosuke Oyama is another intern from Tokyo Tech. We are still working together on some of our convolutional, distributed convolutional problems. Brian Van Essen is a lead of the overall project, and we also have several software engineers as well. So before going into details, let me just give you a brief, very simple overview of what the training of neural network does. So basically, it's iterative computation with some mathematical computation within iteration. And each computation is, relatively speaking, simple linear algebra using some like gems or kind of gems like convolutions. There are work on using sparsity within the convolution, but that's not still not something we are working on, so I'm not going to talk about it this time. In the overall training starts like this. If you have a bunch of data sets and you get only some of them, and some of the data set, the partial data set is called MVAPICH, and we read that, and that's a computation of the layers along the neural network from the top to the bottom, and then go back from bottom to the top, and just repeat this iteration until you get the reasonable accuracy over some fixed number of iteration, and declare it converge. So this is a basic flow of the computation, and the LBANN is basically, it started as an MPI program. So it's compared to other frameworks, it's relatively simpler to use on machines like supercomputers, because this is pretty much the same as standard MPI programs. Written in C++, use MPI, starts with MPI init. And we are using MVAPICH on our x86 machines, as well as our new machines. We started using MVAPICH as well on our Power 9 Coral systems as well. So the reason we are developing LBANN is, one of the reasons is that there are the training is extremely compute-intensive task. You cannot just throw in many, but you cannot just throw in many number of CPU or GPUs. You need to be more clever. You need to develop better way of parallelizing the training algorithms. So these charts show that the demand of the computation is growing very rapidly, and there's successful studies to use a large number of GPUs, but those are not necessarily usable in practice, and we need to come up with different types of parallel algorithms. So that's why we have a series of work that develop the more generalized parallel convolution. So if you may have had of the things like a sample model parallelism. The sample parallelism is that the one you show on your left. Basically, you have a mini batch, some number of samples, and you distribute the samples, training samples to multiple CPU, GPU nodes, and you do the same computation on each processing element. The only thing you need to do in terms of communication is just reduce the gradients in the backprop. So this is typically done with any of the existing frameworks. So if you, for example, download or TensorFlow or PyTorch, and using that with the communication substrate like a NICO or MPI, and you get this parallel training. But that's not the only way to parallelize this computation. You can also parallelize in the different dimensions. One is the spatial parallelism on the middle. I'm going to talk more details about this in the later part of this talk. We recently present at the IBD Fest this year. And also there's another way of parallelizing, which we call channel filter parallelism, which is basically partition. There are multiple channels filters, so we can also exploit that dimension to parallelize the computation, which is also going to be published at the this year's SC. So why we need this type of new algorithm? One of the reasons is that at DOE, we have not necessarily completely unique, but we have scientific data sets that are typically much larger than the data set you see in the typical image recognition problems. So this is pretty much the same what one of the previous speakers mentioned, that on GPU you have, when you want to do training, you may have the limitations of the GPU memory capacity, and you may not be able to just use GPU, and you may need to use CPU. But there's a good reason that GPU only has some limited capacity of memory, because with HBM, it's probably not economically feasible to have those CPU-like capacity on a single package yet. So, but if you have machines like Sierra, in overall, you get one node in Sierra. We have 4 volatile V100 GPUs. Each of them has 16 gigabytes of memory. So in aggregate, we have 64 gigabytes of HBM memory space. Whereas if you only look at one GPU, you only have 16 GPUs, 16 gigabytes of memory. So you may be only able to train a very small network. But if you can use them in an aggregate fashion, there's no such limit. So that's why what we are doing here. These images show some of the example problems we are working on. The mesh tangle detection. This is a snapshot of CFD simulation. There's a AML adaptive mesh refinement going on for this simulation. And we need to periodically look at each of the mesh to see whether we need to further refine or maybe coarsen the particular mesh. But that's a very time-consuming and labor-intensive task because it's not completely possible to automate. But the researchers at Livermore were looking into whether neural network can be used to, at least to some extent, automate the task of detecting the tangling a mesh. And but the challenge was, because this is a scientific simulation, we get the size of the image is like 1,000 by 1,000 pixel. That's much higher resolution compared to maybe 100 by 100 cats and dog pictures. So it has had a problem of the limited memory capacity when you want to train on GPU. Similarly, if you want to apply neural network on the again, the scientific simulation, your data sets may have higher dimensions. In this case, we are working with our collaborators at the Lawrence National Lab. They are doing cosmological simulations. They want to predict some of the cosmological parameters out of the volumetric simulation snapshot. Again, because this is in this particular case, it's just 128 by 128. So it may still fit in one GPU memory, but they are also generating simulation results that's like a 500 cubic data, which did not just fit on the just one single GPU memory. So again, as I discussed in one of the previous presentations, these limitations are a very important problem for the problem we see where we want to apply neural networks in scientific simulations. So one way to work with those large data sets, large samples, is you may wonder why not just partition into smaller chunks of data sets. So let's say you have some cosmological simulation is going on. It generates 512 cubic data sets, and you have some labels here, and you want to train a neural network with these data sets. But you may have a memory capacity problem. So why not just split into, let's say, 128 cubic? I only show 3 of them, but basically you get eight of these smaller sub-cubic data sets. And you can train a model with them. So in this case, our model is some regression model. You want to predict some floating-point number. But those cosmological parameters may depend on some long-range distribution of some of the cosmological matters. So in that case, if you partition the original data sets into smaller chunks, your neural network won't see those long-range behavior. So our expectation was that if you do that, if you just partition them, you get worse accuracy in your regression model. And if you just train a model without doing the partitioning, you get the better accuracy. But that was not possible because on GPU, you cannot just run on this training because of the memory capacity. But if those problems do not exist, what we could see. So this is our preliminary results. And there are 2 charts here. Left one is training accuracy, and right one is the validation accuracy. Basically, the lower is better, and the x-axis is a number of epochs. You can understand that it's just a number of iterations. So the green dots show the previous results. that you get by partitioning the larger sample into smaller chunks. And the pink ones show the accuracy you get if you can train the model without doing partitioning. So we get about order of magnitude better, lower error, which means much better accuracy. So this was a very exciting result to our collaborators at Lawrence Berkeley. And also, we also worked on the mesh tangling problem I mentioned before. In this case, we use the 1,000 by 1,000 training samples. So in this case, we use the semantic segmentation network, which we were able to fit in just using one GPU for one sample. But because of the size of the spatial dimension, if we use more GPU, we get up to 4x faster training performance. So this is, in this case, we use up to 8 GPUs of the LBANN system, which is a smaller version of Sierra, the same Power 9 Volta GPUs. When we use 16 GPU, the speed up is basically saturated. This is understandable that considering that this is a completely strong scaling problem. So we didn't expect that to get the linear performance improvement. But still, if you have enough GPUs, you get a lot faster training time. That's exactly what we wanted to achieve. So let me give some more details about training, parallel training algorithms. Here, in the neural network, we have been focused on convolution in particular, because that's pretty much in all cases it's most time-consuming part of the network. In the convolution, the input is the training samples here, and you have any number of images some spatial size of h times w. In this case, I just show the example with two-dimensional data, but that may be three-dimensional data sets as well. And we have filters that are going to be applied to each images, and you get the same number of output images, but with a different size of number of channels, and also the spatial dimension may change depending on your configuration of the convolution. So the most common way to parallelize this computation is to split the set of images into multiple partitions, which we call sample parallelism. This is the same as in the commonly called data parallel training. In this case, we had set of images, and we partitioned to two sub-partitions. Each of them has two sets of images. And naturally, in ideal case, you get 2x performance improvement. So these are almost all of the frameworks implement. But as I mentioned, there are two main limitations. One is the limited memory capacity. You cannot, each sample itself may be too large to fit on the limited memory capacity of the accelerators. You may be able to use CPUs instead, but then you won't be able to exploit the better performance of GPUs or better memory bandwidth out of those high bandwidth memory systems. And another problem is that because in the sample parallelism, you basically partition mini batch, which has samples, n samples, and obviously you cannot extend your parallelism beyond n. If your mini batch size is, if your mini batch has, let's say, 128, then you cannot use more than 128 GPUs. That may be okay for most of the case, but if you have large machines like Sierra, you may be able to throw in more GPUs, but that's not possible with sample parallelism. And you may wonder, why not just use large mini batches? There are some successful case studies showing the good performance using large mini batches, but generally speaking, there's a accuracy problem which is not yet solved. And if you arbitrarily increase your mini batch size, your resulting accuracy of your model may be lower, or may get similar accuracy, but you may need more iterations to converge. So if you see the performance like number of image to be processed, that won't say anything about accuracy, actual accuracy you get in the end. So your computation may be faster, but you may actually need to run more iterations, and which sometimes which may not be actually worthwhile. So in practice, the n here, the size of mini batch is around hundreds to maybe 1,000. But on Sierra we have more than 10,000 GPUs. So what we could do with the rest of 9,000 GPUs. So that's why we will explore the different dimensions of parallelism. This is the sample of parallelism I showed just before. And you can also cut the problems, your input problem into, like the case here, into the horizontally partitions. So each rank 0 is going to have just a top half of the images, and rank 1 only has the bottom half of the images. And similarly, the output of the conversion, in the rank 0, you only get the top half, and the rank 1 has the bottom half. So again, in the ideal case, you get 2x speed up. But reality, the efficiency of computation may be different. So I'll show you some of the actual example in the later. But basically, the parallelism here is not just limited to the sample dimensions. We can also exploit the spatial domains to parallelize. There's one thing we need to do, in addition to just cut into multiple pieces, is that we need to do basically header exchange for convolution. Because the conversion requires, it's pretty much the same as a stencil in the PDE type of computations. You need some neighbor data. So for the interior points, should be fine. But for the boundary data, you may need to get data from the neighbor GPUs. So it's the same as a stencil or the typical header exchange patterns in scientific simulation code. There are also, we need also take care of the some variations for pooling and backdrop, like what we call reverse header exchange. But these are basically the same communication pattern in the stencil header exchange. And the sample and the spatial parallelism, they are orthogonal. So we can use both of them in the one single training as a hybrid parallelism. One example would be is that we first use sample parallelism of the mini-batch size of n, and then we can further partition the problem into multiple subproblems by using spatial parallelism. So on Sierra type of systems, we may do first, let's say the user of LBANN may want to use particular mini-batch size because they know that this size of mini-batch works most well for particular network. So let's say that's 64. Then we may use 64 nodes to parallelize on the along the sample dimensions. And then, but each node has 4 GPUs. So we may use those 4 GPUs to parallelize one sample of problem by using spatial parallelism. And within a node, we have NVLink performance, the link communications. So we get the much lower latency as well as the higher bandwidth. So while the hair exchange is not trivial in terms of communication cost, we may be able to exploit the higher bandwidth, lower latency within internal GPUs. So let me say a little bit about the implementation. We extend the LBANN toolkit with the tensor computations package, and we use the aluminum for communication. Aluminum is a kind of wrapper around MPI or nickel or any kinds of communication backends. We add some extra features that I'm not going to talk about in detail here, but if you are interested in this also gave us a better performance than just using MPI. These are the performance results using spatial parallel convolution. This is just one convolution of 1,000 by 1,000 image with 16 channels, 16 filters. If you use just one GPU, it took in our system, in particular CUDA library, about 0.5 milliseconds. And we compared Spectrum MPI, MVAPICH GDR, and we also use aluminum as well. Aluminum works like a GPU direct async features, so it gives us better performance compared to just using standard CUDA-aware MPIs. But we are currently looking at using MVAPICH GDR inside aluminum so that we get better GPU direct RDMA performance, and aluminum is CUDA stream synchronous communication semantics. So this is overall training performance. This chart shows a mix of weak scaling and strong scaling performance. If you see each line in a horizontally, it shows a weak scaling. This is a training time for the mesh tangling problem, where we use the 2048 by 2048 training samples. And this won't fit in just one GPU, so we need to use at least 2 GPU for each sample. The spatial parallelism was necessary here. And we get the excellent weak scaling performance. And also, if you look down vertically, that shows the strong scaling performance for a given mini-batch size. So the resulting model should have the same accuracy because we do the mathematically equivalent computations, but we can throw in more GPUs, and if you do that, we get up to 4x speed up compared to just using 2 GPUs. So in conclusion, I think I hope that you get some idea why we are doing yet another deep learning framework that was necessary to work to solve some of the important problems we are facing at DOE labs. And the two things are limited memory capacity problem, and also we want to scale the performance using a large number of GPUs. That's implemented in LBANN. Of course, you can download and install with SPAC. And we also have interesting ongoing work and future work as well. Some of the new work will be show up in the SC19. And you can find more details about our work, previous work in these references. And I'm happy to take any questions. Thank you.
Okay, so let's try to